Hi everybody. I'll try and make this short and sweet so we can get to lunch in 4 minutes, or maybe 14. We'll see here. So I'm going to talk today about tile drainage and tile drainage management, and we'll just look quickly here at a typical conceptual model for how tile drains work. And what you see is the elliptical water table sloping towards a tile drain. This is a tile drain in a free drainage condition, and the gradients and the preferential flow pathways in the vicinity of the tile create kind of a rapid capture zone around the tile that allows the tiles to capture surface applied solutes and deliver them to surface water in a fairly rapid fashion. As you move away from the tile drain, the surface applied solutes present perhaps more of a risk towards the groundwater resource. So tile drainage, I'm from Ontario, and why do we worry about tile drainage up in Ontario? Well, half of our really productive agricultural land is tile drained. Tile drainage is increasingly being used, so more and more land is being tile drained, and the tile drainage is becoming more intense, meaning that the spacing between drains is shrinking. And today I'm going to talk about a study that was conducted out near Ottawa in a macroporous clay loam soil where half of the field was under free drainage, where the drains were just left in an open state, and half of the field was managed with controlled drainage. So what you see on the right here is a controlled drainage structure with gates put in place to block the discharge from the field until the water level reaches a certain prescribed elevation, which is set by the gate elevation. So up in Ontario, we utilize this practice. So free drainage is typically what the fields are in between harvest and spring. That allows farmers to get onto the fields earlier, improves the soil aeration, and reduces the amount of surface runoff. So by raising the water table then during the year with controlled drainage, we can hopefully conserve water and nutrients in the root zone to promote plant growth. Now, it's important to realize here that we talk about reducing surface runoff by lowering the gates and the control structure. By reducing surface runoff, we're also hoping to reduce the losses of phosphorus via surface runoff. So from there, we start thinking, okay, why is tile drainage management a relevant BMP to talk about now? Well, across the U.S. Midwest, NRCS has identified approximately 30 million acres of land that's suitable for tile drain management BMP implementation. So any subsequent effects that tile drain management can have on groundwater need to be understood. It's a process that's targeting surface water quality and specifically nitrogen in surface water. And the thought is by controlling tile drainage or reducing the amount of tile drain discharge, you're reducing the amount of nitrate movement off of the fields and into the surface water. And it's kind of a one-to-one ratio. If you can reduce your discharge, you can also reduce nitrogen loads to the surface water. So I mentioned this is a talk about a field experiment. So here's the field site, and what it is, it's 100 meters by 100 meters field area with 6 tile drain lines, 3 of which are in a free drained condition and 3 of which are controlled. Tile drains are about 80 centimeters deep, spaced 15 meters apart, and we set the overflow level in the control structures at 30 centimeters below ground surface, and there you can see in the bottom the control structures across the field. This is also a very heavily instrumented site which supported some of the modeling I'm going to talk about. So here's the manure application, and if anyone wants to leave for lunch now, there's a conclusion you can draw from this picture. Just off to the right, you don't see it, was my wife's Honda Civic. Never park your wife's Honda Civic downstream from a liquid swine manure application on application day. If you want to take anything home from this talk, that's a good point, because that was also the day I inherited a Honda Civic. So the manure was spiked with rhodamine. We applied it with a surface broadcast application, and we put it on a fairly heavy dose, so 80 cubic meters per hectare, and that's a little bit above the agronomic level you might use, but it gave us a good signal to track. So here we are, and that's what the field surface looked like after we applied our red manure, because of the rhodamine tracer that was applied with it. So here is, so this is macroporous soil. This isn't the exact soil from the site, but it's typical of the site. It's kind of like a Swiss cheese where you've got these abundant vertical worm burrows that create very rapid transport conduits for surface applied solutes to get down into the subsurface. And at the site at Winchester that I'm talking about, these features, they consist of root holes, worm burrows, desiccation cracks, and structural characteristics within the soil. So now, just briefly, we're going to look at some results from the field study. And the blue bars, that's the precipitation. So this is a 36-day monitoring period. We get periodic precipitation, and we're looking at the discharge out of the control drain plots and the free drainage plots. And as you can see, the free drain plots flowed continuously over the 36-day monitoring period. There was an increase in response to the incident precipitation, and the control drain plots flowed periodically. But during the precipitation events, the discharge from the control drain plots was quite significant as well. Over the entire 36-day monitoring period, the free drain tiles captured about 80% of the incident precipitation from a volume perspective, whereas the control drain tiles captured 36%. So we'll now look at the results from the field study where we're tracking rhodamine and nitrate. And this is quite interesting. As would be expected, because the free drain tiles were flowing at the time of the manure application, we see an immediate breakthrough of the nutrients at the tile drain. Within like an hour, we had the manure constituents coming out the drain. Whereas from the control drain plots, we didn't see any nutrient or rhodamine breakthrough until the first precipitation event that occurred following the manure application. But when that breakthrough occurred, the concentrations were actually higher from the control drain plots. And because the tile drains were also flowing at the control drain plots at the point when the precipitation occurred, there was no significant difference in actual mass loading between the controlled drainage and free drainage plots over this 36-day monitoring period. And as we can see, we looked at the flow-weighted mean concentrations at different time intervals, and consistently the concentrations were higher coming out of controlled drainage as compared to free drainage. And another interesting anomaly we observed is this big spike in nitrate concentration about 35 to 36 days after manure application at the control drain plots that we didn't see at the free drain plots. So, and those types of trends are also translated down into the shallow groundwater. So here we're looking at groundwater rhodamine and nitrate concentrations at 1.2 and 2 meter depth. And we see the concentrations for the tracer are higher beneath the control drain plots. And we again see a nitrate spike at the later time at the control drain plot. So there's some interesting things going on here. And we can infer that the downward transport is faster underneath the control drainage plots. So the field results are interesting. They're a little bit puzzling. So we thought, okay, to really get a mechanistic understanding of what's happening, we'll use a model. So we used the fully integrated reactive transport model that has dual continuum or preferential flow and transport considerations. We invoked some pretty complex boundary conditions. We incorporated the viscosity influences from the manure run flow and transport. And we incorporated nitrification and denitrification. And here's a cross-section through our model domain. So this is a two-dimensional slice through the field. You can see our liquid application surface was on the top. And won't go into a lot of detail here, but we try to incorporate as much of the soil structural characteristics as possible. So we have the different soil horizons, macroporous where they need to be. We have a low permeability plow pan. And we also coupled the two-dimensional domain here with the regional groundwater flow system. And that turned out to be a very important attribute of this model in order to represent how both controlled drainage and free drainage are influencing the flow system within the tile-drained fields. So why consider macropore flow? And there's different ways to parameterize these hydrologic models. If you're not looking at reactive transport or solute transport in general, oftentimes people will use like a bulk soil hydraulic property representation where you take kind of an average permeability that composes of both the macropores and the soil matrix, and that's fine. You can kind of reproduce hydrology, but if you're looking at transport, you really need to implicitly represent the preferential flow pathways, and that's what we did here in this model. Why consider the soil structural characteristics? Well, there's a couple ways to look at uncertainty in hydrologic models. There's parameter uncertainty, which is what we don't know about the permeabilities and the porosities and like the physical characteristics, but then there's also structural uncertainties, and that really relates to how well can we actually define the physical system. So by incorporating all these structural characteristics, we're hoping to reduce the structural uncertainty in the hydrologic model output. So, and you can see here just by including a soil plow pan or a low permeability layer between the topsoil, we can have a significant amount of influence on how the model predicts the ammonium, in this case, to be dispersed through the soil profile in response to different manure application methodologies. And now we look at the model performance. Here we're looking at the hydrology, and the model could reproduce the hydrologic characteristics from both the controlled drainage and the free drainage scenarios very well. The amount of water that was captured by the two different drainage scenarios in the model, very close to what was actually observed at the field site. The timing, the magnitudes of the different spikes across the 36-day monitoring period, they were also very well reproduced. So hydrologically, the model worked pretty good. From a chemical transport perspective, the model also worked pretty good considering the inherent complexities with this type of a simulation. I mean, there's nitrification, denitrification happening here. The nitrate that we're actually tracking is produced in the model via the nitrification of ammonium, so that was also configured into the reactive transport component of the model. And we see the timing and the magnitudes are reasonably well reproduced for both free drainage and controlled drainage. And what's really interesting here and important to point out, probably the most important thing on this slide, is to see how the model reproduces the late time nitrate spike in the tile drain effluent from the controlled drainage situation. So that was one of the anomalies we wanted to use the model to try and sort out. So now we'll look at kind of a cross-section through the simulation domain at different times. So this is 3 days and 36 days after application for the free drainage and controlled drainage scenarios. And what's interesting here is, and this is one of the this is going towards one of the conclusions we're getting at, is that there's this upwelling of groundwater in the free drainage scenario in the vicinity of the tile that's acting to dilute the concentration of the surface-derived solutes. Whereas under the controlled drainage situation, the water table is consistently higher, and then there's less ability of the shallow groundwater to upwell. And if this is the end of the talk, oh, here we go, okay. Influence of hydraulic gradient. So we simplify now what we saw with the model results into some cartoons, and in context now of the original conceptual model that I presented, which is kind of the traditional conceptual model for how tile drains work in the natural environment. Now we've kind of added a groundwater component to the free drainage scenario, and what the model really allowed us to do was highlight the importance of this shallow groundwater upwelling in the free drainage scenario that acted to dilute the solute concentrations, whereas in the controlled drainage scenario we kind of have a uniform downward movement of nutrients, and the tracer that is largely a function of holding that water table higher. Another, if we get to the next slide, good. Another one of the things we were able to elucidate with the model was the influence of diffusive mass exchange between the soil matrix and the macropore domains. So by lowering the water table in the vicinity of the tile in the free drainage scenario, we reduce the amount of intercontinuum mass exchange, whereas by holding the water table high, we have kind of a hydrostatic condition between the soil matrix and the macropores, so then mass can more readily diffuse between the two continuums, so then we can effectively leach mass out of the soil matrix into the stagnant macropore domain, and the macropore domain under the precipitation events is really what's contributing to the tile drain flow. So this is another one of the phenomenons that we were able to tease out of the model, which explained this concentration anomaly we observed in the field data. So from there, we'll get to the conclusions, and we can say definitely tile drain management, the implications on groundwater, surface water interactions, it's not a simple thing to think about, and under different scenarios, these systems are going to behave differently. The influence of surface-derived solute migration to surface water under different drainage management regimes is also not straightforward. Tile drain management, it will definitely increase nitrate loading to shallow groundwater, which is potentially a consideration if you're in an area of vulnerable shallow aquifers. And also, it's important to note, so this whole experiment and the modeling was based on, trying to reproduce a field experiment where manure was applied. And even though there are some longer-term repercussions for tile drain management, we did show that you can eliminate that rapid movement of manure constituents out into surface water by blocking the tile drains at the point of application. And while this talk focused a lot on nitrate and the dye tracer, for certain, under all scenarios, we noticed that controlled tile drainage was able to reduce bacteria and pathogen loading to surface water. So even though the concentrations for the solutes came up a little bit for controlled drainage, the bacteria and the pathogens, those concentrations were actually in line with what we observed at free drainage, and because of the lower flows, we had lower bacteria loading. So with that, I'll take us to the final slide, if we make it, and there's some literature if anyone wants to dig deeper into what transpired over the course of this experiment.
Steve, thank you very much. What a question for Steve.
Thank you very much for this presentation. My question is about the project. It wasn't clear to me whether or not your project and the experiment and the control drainage was designed to also provide irrigation water and nutrients perhaps to a crop that is being grown on the field, with the possibility to remove some of that water and the nitrogen. And that's one. And second, if the water levels were managed and adjusted based on the crop cycle that is being grown on the field, with the opportunity to provide some of the irrigation and nutrients for that particular crop, and not just for the drain water movement.
Yeah, so this experiment was run, it was run in October up in Canada, and we only grow one crop per year. So this was on a fallow field. There was nothing growing, and we were just really looking at the efficiency of controlled drainage. Like, the hypothesis was, if we block the drains and hold the manure in the field, we would also hold the manure constituents in the field proportional to the amount that we can reduce flow. But we didn't observe that for nitrate and the rhodamine tracer. But this was a late fall, post-harvest application.
One more?
Yep.
Interesting to see, Steve, your results of controlled drainage, and especially I like the influence of upwelling groundwater on diluting the concentration in free drainage. Now, on the controlled drainage, you talk about that it holds the water back, so it cuts down some drainage volume, and you made a comment that would migrate the nitrate to the groundwater. When I work in Iowa, I was told that that migration of groundwater to the nitrate to the groundwater helps it to denitrify in the pathway in the drainage somewhere down the system. Any thoughts on that in your situation?
Well, yeah, so and you would expect more denitrification in the controlled drainage scenario. We didn't really observe that. But the story's still out on that. So we've got some reactive transport, like some really detailed multi-phase reactive transport going on right now to look at the influence of the preferential flow pathways on oxygen in this system. And we think we might get a little bit more insight into what's happening with denitrification by like a multi-component, multi-phase reactive transport model. But yeah, you're right. You would expect inherently that you would see more denitrification under controlled drainage. The one thing, I didn't really go into a lot of details here about what the hydraulic gradients were under the precipitation events, but when we have rain at this site and we're blocking the drains, the water table gets very close to ground surface, and there under that dynamic kind of a transient response of the system, we drive more of the solutes down into the groundwater under controlled drainage. So there's definitely a more rapid movement of solutes into groundwater under the precipitation events when we're blocking the tiles. And I think that might have had something to do with the higher nitrate levels as well.